I'm so excited. It's time to do a math problem. And who doesn't like to do math problems in physics? Exactly, nobody. None of you raised your hand because we all like to do them. Here we go. This is a Coulomb's law problem that I really, really like. You know what I'm saying? Yeah, I hope you do. I hope you're getting it, okay? I like this problem. Here we have 3 charged particles. A positive 2 Coulomb, a negative 4 Coulomb, and a positive 8 Coulomb. I made them as Coulombs to make the math easier. Of course, boy, you don't want to mess with those. If those are real life things, that would be like, dead. That's a lot of coulombs, a lot of charge. Most of the time when we're dealing with coulombs in IRL, be like you and I, like if we're driving down the street, and it's winter, nice dry day, and we have cloth seats, and we get out, we're rubbing our butt on the seat as we get out, and we touch the door, oh, tingly inside. Yeah, you get tingly. Or if you're shuffling your socks, feet along the shag carpet and you touch a metal shelf, tingly. Yeah, those are microcoulombs, or even nanocoulombs. Those are little amounts of, this would be a lot of wah. But I wanted to use these instead of micro and nano just to make the math a little easier to do. We can do a lot of the math in our head without a calculator, even though I do have one handy dandy notebook just in case. So here's the thing, here's a problem, okay. So we got 3 charged particles, positive, negative, positive. The question is how much overall force does this particle feel as a result of these other 2 particles pushing and pulling on it? Now they're all pushing and pulling on each other, but the question here is how much force does this one feel as a result of being pulled by this one, because they like each other, right? They're opposite. And this one's being repelled by this one. This one says, you, yuck, get away from me. So this one's telling this one to get away, while this one's attracting. And so what we want to do is feel the overall force as a result of those 2 forces acting on this particle. I don't know. We've got charge. We've got distance. We want to know forces. Sounds like Coulomb's law. We all know Coulomb is K, Q1, Q2 divided by R squared. Okay, so that's the law that we're going to have to use. We've got charges, we've got distances between them. Let's dive in. The first particle here affecting this particle is affecting this particle. So let's just pay no attention to the man behind the curtain. Just forget this one for a second. Let's just see what this particle does to this particle. Okay, so we're going to go ahead and use our law and plug the numbers in. So the force exerted by these 2 on each other, actually Newton's third law says you pull on me, I pull on you the same amount of force. So let's use Coulomb's law to figure that out. So 9 times 10 to the 9th. We all know, think German, 9. That is Coulomb's constant. All right, so the electrostatic constant. So now the charge is positive 2. This charge is negative 4. I'm putting those in there to make a point here in a minute. The positive and the negative. We're going to divide by 1. Oh, don't forget to square it. Squared. All right, let's do the math. We all know that 1 times 1 is 1, or at least we hope we do. And then this is 2 times 4, that's 8. And 8 times 9, okay, 8 times 9 is 72. We all remember our multiple choice tables. Mrs. Weimar, 3rd grade math teacher, would be proud of you. Okay, so this is times 10 to the 9th. Now, this makes this. This is a negative and a negative. We'll make it a negative. And I'm going to move the decimal place from here to here. Slide it over 1 spot. So I'll have to change this to a 10. So the answer would come out to be 7.2 times 10 to the 10th. Newton's that is a butt ton of force. We've got 2 very, very highly charged particles only a meter away from each other. A lot of force, people. That's a lot of force. All right, there will be strong fields generated by those, and it'll make your head just go, okay, all right? All right, now. So that's the amount of electrostatic force that this one and this one are putting on each other. We're forgetting about you just for a minute, okay? We'll pay no attention to this man yet, but we will. The negative means attraction. That's what that negative means. So the negative means the force is an attractive force. So attraction, that's what that means. So you know that a positive and a negative will be attracted to each other. This one says to this one, come to me, all right, and vice versa. So that's what the negative means. Now, what I'm going to do, though, is when we are going to subsequently come back, we're going to use this. I'm going to keep this on the board. We're going to use this. I'm not going to use the negative in the next calculation. I'll show you why in just a minute. But just know that the negative means it's an attractive force. Okay, that's what we need to know. We're not going to use the negative in any math that we use from this point on, just to be aware of that. But I'll leave it there for now. Okay, so now we pay attention to this man behind the curtain. How much force of repulsion, because positive and positive, they don't like each other. How much force of repulsion does this one have on this one and vice versa? So now we're going to pay the attention to you. We're just going to focus on these two charges here, this one and this one. How much force of repulsion do you have